Section 1.3 is basically an intro to section 3.1 because in 3.1 we actually solve these things. We actually have mathematical models, we have real world applications, and we can do the solving. We can't do it yet because chapter 2 is how to solve a first order differential equation, more or less, and that's the kind of differential equation we'd have to solve here. So right now, this section is really just for the setup. So this functions really well as an intro to section 3.1 where we actually do the solving. So this will involve a differential equation because we're talking about a rate. So suppose the rate, right, there's the giveaway that we're going to be talking about a differential equation, at which a population grows or decays, right? So increases in size or decreases in size. Is proportional to the size of that population. So you can use a first order differential equation. You can see it in that second paragraph. The first order differential equation that you would use right, to mathematically represent this relationship. So the dx dt equals k times x, where k is some constant. K might be positive or might be negative because dx dt could be positive or negative, right? You could have growth, where then you're thinking, okay, it's a positive rate of change. Decay is a negative rate of change. And then x itself, in the dx dt equals k times x, x probably can't be negative. That's probably an amount, right? So that's something that can't go below 0. So probably what that means then is that in order to get a negative rate of change, you're going to have a negative constant for k. So that'll happen, right? Because we're definitely going to have a decay being something that comes up in here. And the models can get a little bit more complex, so I try to arrange this so they get more complex as you go through it. Certainly the brine ones at the end, those are a little more elaborate than maybe the decaying of the radioactive material at the beginning. The first example is growth. So the population of a bacteria culture is growing, so increasing in size. So you think, okay, positive rate of change here. And it's this scenario where the growth rate is proportional to the size of the population, to the number of bacteria present at time t. So this is pretty much just what's there up above where this example is in the notes. So if P is the population size at time t, right? I needed some kind of functional representation here. So I went with P for population. I guess you could have done B for bacteria and said B of t. There's nothing wrong with doing that. But I had to pick something, so I went with P. So then this would be that dP dt equals k times p if I follow along with what's there up above, which is essentially what you want to do here. I guess I should mention that k is called the constant of proportionality, so I'll kind of write that in off to the side here. So k is called the constant of proportionality. And we said that k could be positive, could be negative. This is growth, so k should be positive, right? So here, k is greater than 0, and that is because we are talking about growth, right? If we were talking about decay, if we were talking about an increase, then you'd have a negative constant. And speak of the devil, we're going to have a negative constant now, because this is decay, right? This is a decrease in size. So if so I used A for amount, I guess. So A of t to get my functional representation for the amount of the substance present at time t. I guess you could have used S for substance, like S of t if you wanted to. But if that's how I'm going to do it, so A of t, so that's the amount present at time t. It doesn't really change what the differential equation looks like, right? The fact that it's a decay, that doesn't really affect that. So it's still going to be the same general setup where dA dt equals k times a. The only thing that really changes is that you would expect k to be a negative number. So I'm going to write that in. I guess I used maroon up above. I'll use it here. So we'll say here k is greater than 0, and because this is a decrease, right? So this is a decay problem, not a growth problem, so we should have a negative k. This one's a little bit different than the last couple. There's a little more that you have to do, and really I guess you have to get to the p minus n, right? So, okay, we have a fixed population size of p persons, so nobody comes in, nobody goes out, fixed population size. Then the time of the rate of change of the number n of those persons who have heard a rumor is proportional to the number who have not heard it. Okay, so if n is the number who have heard the rumor, and we're talking about the rate of change of that, you think that's going to be a dn dt. It is. But then that's not proportional to n, because n is the number who've heard it. It's proportional to the number who haven't. So that's why I've got this p minus n in here, right? I need a way to write that out. But if n is the number who've heard it, p minus n has to be the number who haven't, because those two values have to add up to that fixed population size of p. So then, really what we've got going on here is that we need that the rate of change of capital N over time has to be proportional. Let's see, can I make the proportional symbol? Not too well, right? It's supposed to kind of look like an infinity with the one n chopped off, so it didn't really turn out too well. That is what that's supposed to be. But that's supposed to be proportionate to the number who haven't heard it, which is p minus n. Okay. So then what do we end up with? I guess I'll turn this back to blue. I think I've got a little more space down here. What you'd have is that dn dt would be equal to constant of proportionality times the number who haven't heard it by time t, which would be p minus n. I think that's the more common way of writing that. One that would be that sort of thing with the p minus n, right, where you have something a little more complex than just like the k times a sort of thing that we had before. There's nothing wrong really with distributing the k, right? And like you could write it like this if you wanted to. But I think this one right here is probably more conventional. So I'll just say more conventional phrasing. I think that's an okay way of putting it. So, okay, a little more complicated this time. Right, certainly more elaborate than just the growth and decay that were in number 1, number 2. This one I pulled out of another book. I thought this was brilliant. So this is totally lifted. I wish I could say that I came up with this on my own. This is pretty clever, but I didn't. So we've got a population of field mice inhabiting a rural area. In the absence of predators, we would assume that the mouse population increases, right, at a rate proportional to the current population, right? Okay, in the absence of natural predators, that's kind of the way that works. But then if there are natural predators, so suppose the owls live in the area, then the owl presence is going to cause a decrease, right? Because the owls are going to eat some of the mice. So now we got to factor that in. So, okay, first thing that I want to point out. So there's one rate here, and then there's another rate here. So the two rates that are there don't have to be equal. Right, so I do want to point that out, right? Those can be two different rates, and that's going to dictate how we're going to end up having to phrase this. Meaning that if the rates can be different, we can't squash everything together into a single term. That's basically where this is going. So those don't have to be equal. I guess they could be. That would be a kind of a weird coincidence, but they don't have to be. Okay, so let's see. If there are no predators, I think we can kind of do an intermediate step with no predators and build it out from there. So with no predators, then I guess if M is the mouse population, I think M for mouse sounds good. So then dm dt would be equal to k times m. So now just that part by itself. If there are no owls, this is just like number 1, basically, right? Because then this is just a garden variety growth type problem. So then I guess I'll just kind of put this off to the side, that m of t is the mouse population at time t. All right. Then what if there are owls, right? So then with owls, we're still going to have a differential equation with dm dt, but now this has 2 components, right? So then we would have maybe something like this. So you'd have, and they're both the mouse population increase and the mouse population decrease are both proportional to m, right? To m of t, or just m in the equation here. So we'd have something like k1 times m minus k2 times m, right? Or I guess you could write it as k1m plus k2m if you view k2 as being a negative number, right? That would be equivalent. But these rates are probably not the same. So, right, so these right here, so I'll just put that in here, that the rates are likely different, right? And I suppose there is a possibility that they could be equal, that you could reach mouse equilibrium, but you don't have to, right? Certainly not. So this is one where I think that's the way that you want to handle it. You want to have 2 separate constants of proportionality, right? So you couldn't just squash it together and basically make it look like number 1 here. But I guess in a way you could, if you said, okay, well, we're going to put this together and then view k1 minus k2 as a single thing, then I suppose that's correct. But you do want to account for both, right? You want to account for both of those rates in here. And so that's why we got the k1 and the k2. Next, Newton's law of cooling, or Newton's law of warming, I guess, if you're going the other way, if you're heating something up. So, according to Newton's law of cooling or warming, this is another one where we can use a first order differential equation, right? We've got the rate at which the temperature of the body changes, right? There's the derivative part, right? It's a rate of change. Proportional to the difference between the temperature of the body and the temperature of the surrounding medium. So the temperature of the surrounding medium is going to be a fixed value, right? So that would be like air temperature, right? Doesn't have to be that air is your medium, but for a lot of things, that's what it's going to be. So that'll be a fixed value, but then the temperature of the body can change, right? I mean, when you heat things up or cool them off, the temperature of the body definitely changes. So, in other words, that's the differential equation that we're going to have down here in the second paragraph. So, T sub m is going to be a fixed value for what we're going to do, right? That's the temperature of the medium, also known as the ambient temperature. So that's what that's going to be. So, right, it's you take the pie out of the oven and set it on the porch to cool off, and outside it's 55 degrees, right? Then there's your temperature, your medium, right? The 55 degree air temperature. That's the kind of thing that we've got here. And we can have cooling, we can have warming, and we're going to have one of each. Okay, so cooling first. So a pitcher of buttermilk initially at 30 degrees Celsius is to be cooled by setting it on the front porch where the temperature is 5 degrees Celsius. So this is pretty close to the thing that I just thought of with the pie. I guess the pie thing, I don't know, maybe when I learned it that was the sort of lead-off example here. But the stuff that we've got here, so the 30 degrees Celsius, that would be your initial temperature. which we don't actually use in the differential equation. We would if we were going to solve it, because that actually factors into the IVP, like what we were doing in section 1.2. So it's probably worth pointing out, like, yeah, you do need that eventually. We just don't need it right now, right? When we get into section 3.1, we definitely use it. But that's the initial temperature, right? And then temperature of the medium is the 5 degrees Celsius temperature on the porch, right? So that we do need right now. All right, so then I guess big T for temperature. It's kind of how I'm writing this out, and then little t for time. So then the derivative of big T with respect to little t for time would be K times the quantity T minus 5, because 5 is our ambient temperature or medium temperature. And then here, K should be negative because the buttermilk is cooling, right? Like, it comes out pretty warm, right? 30 degrees Celsius, but you put it out on the porch where it's 5 degrees Celsius, it's going to cool off. So that means if the temperature is decreasing, you should get a negative rate of change. So this is one where we should have K less than 0 because this is cooling. And then I suppose you know what happens next. If we have one that's cooling, then we must have one that's warming up, which is certainly what typically goes on when you put things in the oven. Well, I guess when you put things in the oven and then turn it on, right? So 4-pound roast, initially 50 degrees Fahrenheit, gets put in the oven at 375, and then after 75 minutes, it's found the temperature of the roast is 125 degrees Fahrenheit, right? I guess when it gets poked with the meat thermometer. So, okay, let's see what we got here. So the initial temperature is the 50 degrees Fahrenheit, right? So T0 is 50 degrees Fahrenheit, which, just like with the last one, we don't need that to set the differential equation up. You would need it in order to solve the IVP, though, if we were going to do that, which we are when we get to section 3.1. 375 is the temperature of the oven, so that would be our temperature of the medium. And then we know that at T of 75, we have 125 degrees Fahrenheit. Also might need that kind of thing when we get to section 3.1. But then if we're going to set up the differential equation, we really just need the temperature of the medium. We just need that 375. And this will kind of look like the last one, except that it has a 375 in it. So D big T over D little t, right? Temperature and then time would be equal to K times the quantity T minus 375. And this one is warming or heating, so you'd expect a positive rate of change, and so that would mean that K should be a positive number, so I'll write it underneath just like I did for the last one. So K greater than 0 because this is heating. Mixtures are a little bit more complex than the ones that have come up so far, and you can see it in that second paragraph. It's still a first order differential equation, but look at this. Look at this that's happening right here with the input rate minus the output rate. Those certainly don't have to match. And the output rate is usually a little bit more involved. So putting the differential equation together, usually the input rate is kind of straightforward, but the output rate involves a little thinking about how to set it up. That's usually the more involved part. And that's going to be very evident in these couple of examples that we've got. And then capital A being the amount of salt in the tank. And it's certainly the input rate and output rate don't have to match each other, right? As long as the tank isn't already full, you could have the input rate being higher than the output rate, right? So then as time passes, there would be more and more solution in the tank, even if some of it was draining out. And then I suppose if it's the other way around, if the output rate is greater, then eventually you drain, you get it down to where you don't really have anything in the tank anymore. All right, so then in order to put the input rate and output rates together, so okay, this right here, this is going to be important because this is basically how you set them up. That's a haggard-looking asterisk. Let me see if I can make that look a little bit better. So yeah, the input rate is not going to be anything too complicated, but the output rate could be. So we'll see it essentially right now. All right, so the first example we've got, so a tank initially has 120 liters of fluid in it, in which 10 grams of salt is dissolved. So that concentration is much less than that of the mixture being pumped into it. So the mixture entering the tank, 1 gram per liter, right? What's already in there when this is beginning is 1/12 of a gram per liter, right? Much less salt than the original mixture. So then you think, okay, well, the salt concentration is going to go up. That's certainly true. Okay, so the mixture that's 1 gram per liter is entering the tank at a rate of 2 liters per minute. And then the well-stirred mixture leaves the tank at the same rate. Okay, that's nice. They match up. It is easier when they match up. That's why this one's first, right? They don't match up in example number 8. So then we want to determine a model for the rate of change of the amount of salt in the tank. Okay, so we need the salt input rate and salt output rate. So, okay, now we can put those together. So R sub in, right, the input rate. So in words, that would be the salt input rate. Okay, so then if we're just looking at the amount of salt, then you think, okay, you want it in grams, but it's a rate, so grams per unit of time, and it looks like the unit of time that we're dealing with is minutes, right? Because we have the enters the tank at a rate of 2 liters per minute. Looks like that's our unit of time. So for the input rate, it's the concentration, which that mixture that's coming in, the concentration is 1 gram per liter of salt, multiplied by the rate at which it's entering the tank, so 2 liters per minute. Okay, well then 1 times 2 is 2, so it looks like we've got 2 grams per minute. And you go, okay, well that didn't seem so bad. No, but also the input rates are usually a little easier. The output rate, that will be maybe a little bit different, although this one is not as complex as the next one, I will say that. So R sub out, which would be the salt output rate. Okay, I guess first we would need to know what the concentration is. So one thing that we do know is how many liters of fluid are in the tank at all times. It's always 120. The reason it's always 120, at least in this case, is that we have the mixture entering the tank at 2 liters per minute, and then there's also some outflow, the well-stirred mixture leaving the tank, also at 2 liters per minute. So at all times, we've got 120 liters of fluid in there, right? If the rates at which a mixture is entering and exiting the tank, if those don't match up, then the amount of mixture in the tank is going to change. But here it's not, because those two rates match. So this is the tougher part right here. The second part is still going to be 2 liters per minute, right? The rate at which the mixture leaves the tank. But then the concentration, that's going to change over time, right? Because what's being pumped into the tank has a higher concentration compared to what was already in there, right? That 10 over 120 is much less than 1, right? So it's going to be whatever the amount of salt is in the tank, where we said that's A, it's that divided by 120, because we know it's always 120 liters in there. At least it is here, right? Because the inflow and outflow are identical. So it would be A over 120 This is the tough part. So if that makes sense, so that it's always 120 liters in the tank because the entrance and exit rates are matching, then it's just whatever the amount of salt is over 120 to get that concentration. But that's changing, right? Really, it's going up, right? Because what's being pumped into the tank has such a high concentration of salt that it's going to push the concentration of whatever is in the tank upward. And then times 2 liters per minute, right? That's the flow of the mixture outwards, right? It's 2 liters per minute again. It does say that in the wording up in the second sentence there, leaves the tank at the same rate. That's where that 2 comes from. And so I guess if I simplify this, I would get A over 60. So A over 60 grams per minute. And now I can put the differential equation together. So then dA dt, if that's going to be R in minus R out, well, now we have those. This will be 2 minus A over 60. And there we go. So the tougher part is putting together the output rate, and you can tell, right? Because then you think, okay, well, there are other things that could happen too. Like what if the mixture entering the tank is coming in at a different rate than the mixture exiting the tank is going out? That's the next example. Okay, so here, same as example 7, except I wanted to have it where the mixture entering the tank and the mixture exiting the tank are doing so at different rates. So the input rate basically works the same way as it did in number 7, except that now it's a 5 instead of a 2. Okay, well that doesn't sound so bad. So R sub in, which will be our salt input rate just like it was before. This is going to be 1 gram per liter, right? Same concentration, right? Everything else is the same except this one rate is going to be different. Times 5 liters per minute. And you'd get 5 grams per minute. Okay, fine. Looks about the same. This will be a little bit different though, the output rate. So R sub out there, that will once again be our salt output rate. And so then that's going to be, well, we know that the second part of this is going to be a 2 liters per minute. That's right. That part's a foregone conclusion. It says it up in parentheses up toward the top. The tough part is right here. So what goes on the bottom? It's not going to be a 120. We still have A on top, right? It's still the amount of salt in the tank divided by the amount of liquid, basically, right? The amount of the mixture. It's not 120. What it actually is, and this might be easier to see if I write it down and then explain it, it's 120 plus 3t. And the reason for the plus 3t is because the difference between the rate at which the mixture is entering the tank and exiting is 3, right? It's 5 minus 2. So really what's going on here is, in order to get this thing, so 1 unit is a minute, right? So what's happening in every minute? We get 5 liters in and 2 liters out. And so that means that the net is 3 liters in, right? That's the net change there, right? 5 minus 2 is 3. So, right, after 1 minute, you'd have 5 liters in, 2 liters out. That's a plus 3. After 2 minutes, it's 10 liters in and 4 liters out. That's a plus 6. Right? Then 3 minutes is 15 in, 6 out. That's a plus 9. Right? So it's 3 times the amount of time that's elapsed. So that is the part that's different this time. And so it's that concentration, and then times 2 liters per minute. And so then this would be, I guess I can't really simplify this because of that 3 in the denominator. I can't cancel anything. So this will be, I suppose, just 2A over 120 plus 3T grams per minute. And then to put everything together, dA dt is going to be 5 minus 2A over 120 plus 3T. And if you're looking at this and thinking, okay, we have a more complex looking differential equation, does that mean that it's harder to solve? Maybe a little bit. But really the thing to be careful of is just more in the setup, I think. Just getting that output rate to have that 3T in it, which we have to do because the rates at which the mixture is entering and exiting don't match up anymore. So we do end up with a more complex setup because of that, but I think that's the key, is just arriving at that setup. If you get the setup right, then once we've gone through the solving in Chapter 2, even solving this one, even though I know it looks more complex than the one in number 7, it's still not going to be too bad.